Alkenes are two sp2 hybridized orbitals, okay, on carbon and next to each other. And that's basically the definition, right? Call them double bonds, usually, because that's just sometimes what we call them. Though that's pretty generic, because lots of atoms can engage in double bonds. But the alkene is an example of a double bond between two carbons. And so if you have a carbon and a carbon here, and we had discussed that in these alkene systems, they're sp2 hybridized. So that means that there are two or three sp2 lobes, right? And then there's a sigma bond. So we can say there's an electron here and here. And then sometimes we'll just say that's connected to an H, and that's connected to an H. And these are all H's, and they're all coming out at you. And then the alkene bits, right? That's the unhybridized p orbital. And that basically is like a carbon radical, if you will, between these. And of course, they don't necessarily have to be right there, I guess. One can be down here. But you have electron density that's going back and forth over this double bond. And that's essentially the whole alkene bit. So the energy formed from the alkene, because in aggregate total alkenes are more stable, but they contain a pi bond here, and that is worth 63 kcals per mole. And they contain a sigma bond here, the sigma bond, and that is worth 83 kcals per mole. And you'll notice that the sigma bond is actually more stable than the pi bond, all right? And so you would come to expect that your pi bond is the more reactive one, because it is lower in energy, all right? And what I've drawn here is ethene, all right? And so ethene, we've discussed, has this configuration where this orbital is actually kind of coming out at you. It's planar, all right? That orbital's going away, and this orbital's coming out at you, and that's going away, and it forms a planar structure right here and here, and then that goes back there, and that's sort of a plane. And the pi bonds exist above and below the plane, all right? And they have pretty well-defined lengths in this system, so this ethene. So double bonds, because they're stronger, they have tighter angles associated, or they're shorter, I should say. And so the actual length, let me redraw the ethene here. How we normally draw it, of course, and more review, hopefully. We sort of draw it like this. All right, and the actual lengths of these bonds. So this carbon-carbon bond is 1.33 angstroms. All right, and that's shorter. So let's compare and contrast. Probably would be helpful if we compared and contrasted it to ethane. All right, so carbon, carbon, H, H, H. All right, and so the carbon-carbon single bond is 1.54 angstroms. All right, and that's compared to 1.33, so it's shorter. These carbon-hydrogen bonds, these are pretty typical bond lengths for carbon-hydrogen. They don't vary too much, carbon-hydrogen bonds. Roughly 1.8 angstroms. I guess this has been measured to be 1.09 angstroms between those two. And then hopefully you appreciate that carbon-carbon angles in sp3 hybridized are approximately 109.5 degrees, and that these carbon angles, these angles right here, are actually a little bit, they're close to 120. They're not exactly 120 though. So this is about 121.7 degrees that goes in here. And because that's a little longer than 127 degrees, this has to be a little bit shorter. And so that's a 116.6 degrees, okay? So not exactly perfect. And these numbers do depend on substituents. So if these were really, really big right next to each other, it would sort of force them apart, right? And so those numbers aren't fixed, but the idea is that in the hybrid situation where these are all 120 degrees from each other, that's what we would call ideal. Of course, in real life, it's not ideal. It depends on a couple things, but they're still pretty close to 120 degrees. All right, and we had discussed that this double bond essentially locks in this geometry. So this orbital right here doesn't want to break. It's conjugation right here. These don't want to break, which means that rotation around the double bond is pretty unhindered. In fact, it doesn't rotate, right? And because of that, you create geometries associated with double bonds. And you're pretty familiar with the geometries. We talked about cis and trans isomers, right? So we would call this, for instance, CH3, CH3. All right. And we can remember that cis, they're on the same side, cisoid, or whatever you want to call it. Cis, this would be cis 2, and this is an important naming convention, butene. All right. Now, how do I come up with this name? All right. First, cis, because it's cis. That's obvious. The double bond is in a cis configuration. And this is a root word butane, right? 1, 2, 3, 4. And the ene is on the second carbon, right? 1, 2. So that's where the ene goes. All right. And, if this were longer, we made this CH2, CH3, this would change what? Hopefully you'd say, well, now that's 1, 2, 3, 4, 5. So now that's a pentane, except there's a 1, 2 double bond at the 2 carbon. So instead, this would be cis 2 pentene. All right. And so the naming convention is pretty straightforward in that case. It's just sort of treated like a functional group that modifies the end of your root. So instead of calling it an ane, you're going to have to call it an ene. All right. And if these substituents, I'm going to put that back there. I'm going to change that back to butene. All right. And if the substituents were on the opposite sides of each other, CH3H, CH3H. All right, obviously the only thing that really changed here, because we've still got, got 1, 2, 3, 4, that's also butene, all right? And that was coming off the second carbon. The only thing that actually changed here is that now these are on opposite. I could probably make that a little prettier. They're on now opposite sides of each other, and that would make it trans. Now, there are other ways of cis and trans naming conventions, and these are from old-timey naming conventions, okay? So if it's a very simple compound, it is usually just called cis-2-butene, trans-2-butene, but when things become a little bit more complicated and you start adding other functional groups, you actually introduce a different kind of more abbreviated way of saying cis and trans. You call them E and Z, all right? And in this particular case, E and Z, if you just break out your German, which hopefully you all still remember from when you learned German, you would know that these 2 carbons are actually on the same side, and auf Deutsch we would say they are zusammen, or together. All right, and if they're zusammen, then that's a Z. And if they're on opposite sides of each other, So zusammen, and if they're opposite, then they would be entgegen. And capital entgegen. All right, that's opposite, and that would be E. So trans is entgegen, cis it's zusammen, and then that is how we would get a name. Now, this becomes more handy when you have something a bit more complicated in your naming convention. So if you go down here and we say have CH3 CH3, and then we put a BR here, and we compare it to this system, right? CH3 BRH. All right. So we have to establish priority on this, just like we do for everything. And cis and trans are not necessarily, the priority is not established by the carbon backbone. It's determined by weight again. So and this is how you determine the priority of the Z and the E configuration, of course, is the priority for bromine is going to be 1. That's going to be 2. And then on this side, it's going to be 2 and 1. And just like this side, this is going to be 1, 2, 2, and 1. So if we look at the 2 highest priority substituents, oops, I screwed that up there. That's the lower priority here. 1 and 1 are on the same side. They are zusammen, and messed it up over here too. There we go. There. 1 and 1 are on the opposite side, so they are entgegen. All right, and then we call this, we name this. Obviously, it's still a butene. And we've got 2 functional groups here. We've got an ene group, so that's going to give that characteristic flavor of 2-butene. And then we've got a 1,2-bromo. That still follows the convention, or it's still alphabetical. 2-bromo, 2-butene, and then we have to specify the geometry of this configuration. Z2-bromo, 2-butene. All right. And likewise down here, since the only difference is now that they are entgegen, we'll say that's 2-bromo, 2-butene. You'll notice that I slash my Z's to make sure they don't look like my 2's. Okay. Nomenclature of alkenes tends to be fairly straightforward in that way. You just identify where they are in that carbon chain, and that's the number you put there, and then you add ene to the end. Of course, IUPAC being IUPAC, everything becomes infinitely more complicated as you just make the molecule larger. But for this course and where we are in it right now, that's the rule that you should try to commit to memory. Okay, now stability, we had touched on. Let's talk about stability here. All right, stability. And if we consider cis and trans or entgegen zusammen stability, our most stable configuration is going to try to be less sterically encumbered. So if you imagine the space-filling models of these, if we put carbon, which we'll say is gray ball. That's a gray ball. Big gray ball, right? Okay, so this is the ellipsoid here, and then we start adding our hydrogens, and of course there's a big hydrogen comes out the front, and there's this other hydrogen that sort of comes out here, and then there's this hydrogen. This is what's called a space-filling model. And so it sort of gives you an idea of how close some things are. I'm actually really impressed with my space-filling model. You can see here that if you do a space-filling model of a double bond, they kind of bump into each other, right? And that is in the context of forming stable systems, not really altogether that great. All right. So the Z configuration, where everything that's big is separated, and bromine, albeit is a bigger atom than carbon, it lacks the substituents that pop out. All right. So in this case, Z configurations, or I should say configurations where the biggest groups. So let me take a step back. Putting the biggest groups opposite of each other is preferred. In this particular case, while bromide is bigger than carbon, all right, it is much smaller than CH3. So if we were to rotate these, you would see plop, that the CH3s, as I've drawn them, this is less sterically encumbered. So the E and Z designation doesn't necessarily indicate stability. What you have to do is use a bit of intuition to see which is the bigger group physically and not by molecular weight. So generally, all right, trans is going to be the more stable configuration. The cis isomer has steric problems up here. So when you look at stability, you tend to think trans is more stable than cis. And that cis and trans configurations usually come simply because the larger group is usually a CH3 or some sort of carbon, because carbon has stuff coming off of it. But don't be fooled by the fact that halogens, while they're big atoms, don't have stuff coming off of it. So that's just a little caveat for you. But in general, we're going to say that trans is more stable than cis. So this is our stability. All right. And that comes from sterics. Yeah, there you go. Stability. Cis better than trans. A clear example is, of course, 2-butene. And oftentimes we don't bother to write the hydrogens here, but we can. The alkenes sometimes look weird without them, in my opinion. And then we can throw in our eyeball of science, because you can actually do a Newman projection with these things. And if you do that, what we see down here are CH on one side, H on the other. And in the back, I've got a CH3, and over here we got an H. And I'm kind of drawing them twisted out of plane. You know, funny, it's actually, strictly speaking, not false to twist them slightly out of plane, but I'm overdoing it because it's really hard to show eclipsed conformations without obscuring a whole bunch of stuff. I guess I could just sort of draw them like this, so it's just a little bit above. That's probably a little bit better. But in any case, you can still see, you know. So consider and think about and practice Newman projections with alkenes as well. Now, we had discussed, right, Zaitsev's rule. So let's talk a bit more about that. And Zaitsev's rule, because we're still on the stability kick. And we had discussed Zaitsev rule. And Zaitsev rule essentially says that the number of alkyl substituents increases the stability of the alkene, all right? And I never really kind of went into it, but let's go back up to this picture, and then let's steal it. And I'll show you why I'm stealing it from up there. Well, I'm stealing it up from there because I don't have to draw it. If I do that, ooh, snap. And there you go. Now I'm going to get rid of the hydrogens because we're going to talk about substituents, right? Substituents coming off of here. And the idea that these are radicals free radicals, right? Because if we remember Zaitsev Rule and we talked about radicals and we talked about radical stability, carbon radicals are stabilized just like alkenes, and that is to say they have hyperconjugation, and that induces stability in addition to the inductive effect. So the electron deficient carbon radical is more electronegative, and so that's frustrating. And so that is always going to be a plus, which means that these are always going to be a minus. That's going to donate electrons through the sigma bond, so that's the inductive effect, and then you have the hyperconjugation effect, which is a through space interaction. Now the Zaitsev rule says that more substitution is better, so if you want to look at the rough equivalence, then ethene is going to be not very stable. I mean, that's pretty bad. And then you start throwing on, so if we just look at it as a chart, all right, so this is Zaitsev's rules quantified, and we just say that the relative energy here is 0. All right, ethene obviously has energy associated, but we're going to just say relative energies in kcal per mole, and showing how much more stable they become as you start adding substituents, right? So if you throw on a substituent here, that increases the stability by, what did I say, kcals per mole? So that's 2.7 additional kcals per mole, all right? If you throw on, and we're going to have to shrink this down because it's going to get a little big. If you throw on 2 substituents, of course, CH3, then you have geometric considerations, right? Trans and cis. Now, I had said cis is going to be less stable because of sterics, but that does, over the single substitution, increase stability 4.2. All right, so this is an increase in 4.2 kcals per mole from these two. Now, if I draw the other substitution, CH3, the trans substitution, CH3, that actually increases it because we get rid of that steric issue to 4.8 kcals per mole. All right, this is starting to get a little too long, so I'm going to start bringing things up a little closer so they're all on the same page. All right, now if you try substitute it, okay, and there's no real geometry in trisubstitution, CH3, 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 and then that's an H, you increase your stability. Oh, I donked up. There's another configuration that is actually sterically a little worse off than trans. Trans is not so bad. There's something called the Geminal Configuration where you have 2 substituents, CH3, CH3, all right? And these are 2 H's. That is actually a little bit better to put them on the same side than it is to put on the same side of the same carbon. So this is what you call, let me write this in tiny print. This is what you call geminal. And when you have the same thingy coming off of the same carbon, it's called geminal, like Gemini, like twins. So see, twinsies. Okay. And granted, those appear slightly closer, but they're actually, that is the one that is 4.8. Slightly more stable to have a geminal dimethyl or geminal carbon than it is to have a full-on trans configuration. The trans configuration really causes the distortion in the pi system. This causes the distortion between these 2 bonds, but does not really affect the pi system. So the pi system itself is a little bit more stable. Now the trans configuration is 5.2 kcals per mole. So you can see that's actually a whole kcal per mole more stable than the cis configuration. All right, the tri-substituted configuration down here now. So now we're back down here. All right. That goes up to 5.9 kcals per mole. So again, it just keeps getting more stable the more substituents and the more crap you add to it. And then finally, the full-on tetra-substituted system. That is a very stable configuration, 6.2. So you can see from here the overall stability ranking as you go up. There is definitely a significant jump from 0 to 2.7. And then there's a pretty big jump when you start looking at just mono-substituted to the trans-substituted. And then the increase becomes a little bit more incremental as you add additional carbons. And that comes from this configuration, all right, doing exactly the same thing that radicals do, or radical stabilization, that as you add a carbon here, and you have that begins to have an H there, and an H there, you can start to do hyperconjugation through that. The sp configuration being a little bit more electron deficient, you end up giving electron density inductively. And so methyl substituents coming off donate electron density into double bonds. And that creates more stability for the pi system if you rationalize it essentially as a stability forming from these two effects, hyperconjugation and induction. All right. Now, what are the actual ramifications of reactivity in double bonds? All right. So for alkene reactivity, we had already discussed essentially that in eliminations, okay, elimination chemistry becomes more favorable as you produce a more substituted double bond. All right. And what else does it affect? So there are alkyl halide systems, for instance, that you can do SN2 chemistry. So if we look at this reaction and we look at it like this, all right. When we compare it to this, okay, and both of these, so this is a really great nucleophile. And this one, that is 40 times faster than that one, okay? So that's 40 times faster. Obviously, that's just from the double bond. And why is that the case, all right? So remember, this has a resonance structure. You can imagine there being resonance when you start pulling this halide off, all right? And then this is an sp2 reaction, or SN2 reaction very clearly. So your transition state is going to look probably a bit like this. An sp2, I keep saying that, SN2 reaction is going to have a 5-coordinate transition state. We've already sort of discussed that. We've got a carbon here, right? And this is your double bond. And I'm going to actually draw the double bond in as the whole conjugated pi system. All right, so bzzz, right? There's a pi system forming right there, or there's a pi system that's right there, okay? And so your 5-coordinate transition state is carbon here, here, and then you've got an approaching and a departing, so this is going to be your departing chloride, and this is going to be your approaching sulfur. What color is sulfur? Sulfur is yellow, right? SH, all right? And so what you see here in your 5-coordination transition state is that there's basically an sp2-like center right here, right? And as you're forming these things, of course, you know that there's a partial negative charge coming off of here. This is a negative charge, right? So this is a partial negative charge here. You have a very strong partial positive charge forming on that carbon as the electrons are starting to separate. You basically just have it's starting to lose electron density on one side, it's starting to gain electron density on the other, but transiently it's going to form just by virtue of the fact that you have a negative charge coming off and a negative charge this way. Electrons have to be moving in opposite directions, which means that what does this do? Come into the rescue. Electron density comes to the rescue right there. All right. So even though you appear to be dumping electron density from a more electron-rich pi system, it's actually stabilizing this transition state. And according to transition state theory, anything that stabilizes the transition state should make the reaction go faster, which is why that is 40 times faster than your typical SN2 reaction. Now, it's worth pointing out that double bonds, and I had mentioned this in a prior lecture, but it's worth pointing out that double bonds, that does not hold true if you are going to do a reaction like this. All right, you just put a vinyl double bond, and I call that vinyl, and this is called allylic. All right, so allylic double bonds, where they are in the allyl position. So let's just remember this is allylic, right? Because it's an allyl. There's a double bond right next to a sp3 hybridized, putatively sp3 hybridized carbon. This is a vinyl position. A vinyl position has the functional group right on the double bond, and if you were to try to do SN2 chemistry here, you would get no reaction, all right? Because you can't do SN2 type chemistry on an sp2 center. There's a different kind of mechanism for this sort of displacement. It is an energetically very uphill reaction. It's by no means SN2 because you can't form the trigonal pyramidal structure that is associated with this, right? So if you have a double bond coming in here, right? So we're going to just do carbon, carbon. You've got pi bond, and then you got bromine, right? And presumably, I've gone donked that up. That's the wrong tool, right? And so bromine's coming off here, and hydrogen is back here, right? So these are active pi systems. So you're not going to be able to come in with a nucleophile. So if we have a nucleophile, where is it going to attack? All right. In this particular case, you've already got a full pi system on the top and the bottom. So a nucleophile, which is by definition electron rich, can't attack at an existing pi bond. That's not the problem up here, right? There's no actual existing pi bond on this carbon. I've drawn it in as a way to illustrate how these systems compete, but I can just as easily erase it. And you can clearly see that's just a typical 5-coordinate carbon. This is not. This is quite different. So nucleophiles really can't approach these sorts of systems. So this sort of chemistry where you have a leaving group, so Br, and you have a nucleophile, there's no real action of attack if that's CH. All right. So there is, of course, a way to do pi addition. So we had discussed somewhat early on that this is a reasonable thing, that if there's an oxygen up there and there's a Br down there, you can have a nucleophile attack, but it won't attack the sigma bond. It won't attack the sigma structure like this is doing, right? See, this is forming out of the sigma. This will have to attack the pi system. And that is a different mechanism. So what is the summarization? The point is vinyl carbons, I should specify, vinyl carbons don't undergo SN2 chemistry. They undergo a different kind of chemistry that we'll get into. And some of them require a lot more energy, some of them don't, but the point is that they don't undergo SN2 type transition states, which means that by virtue of the fact that there's no way to stabilize a cation on here, it means vinyl carbocations are trash, all right? So you don't form vinyl carbocations. That's your other lesson. Now, what does this mean in terms of reactivity? All right, so let's put the Here's a couple of them, and then we're going to put the bromine on a couple different places. Let's put a bromine here, and we'll put a bromine here. I'll stick a bromine here. And let's put a bromine here, and then let's put the bromine here. All right, so we can now check these down. All right, let's consider the relative stabilities of these reactions. The most reactive one is going to put the bromine on a position allylic to the double bond. So that would be either this position or this position. And you see you've got one right here. All right, and you got one right here. And of course, the most stable formation of a if we're just going to look at this strictly speaking from SN1, right, this makes it simpler. Because in SN1, that's all about how stable of a carbocation can you form. All right, and the most stable carbocation formed is going to be one which puts the positive charge on a secondary carbon in a vinylic position. Followed by that is going to be just a vinylic position. All right, that's going to be a good place for a carbocation. And then these substituents essentially look at, all right, this isn't vinylic, this is now fully separated from the carbon, but it's still a secondary position, which means it's pretty good. And then this is a primary one, so this isn't going to form a carbocation at all. And then this is a vinylic position, so it's going to form a carbocation, even not at all, even more. So it is desperately disinterested in forming any sort of carbocation. So there you go.